So, good morning. Let's start. We're talking about reliability of systems, and reliability analysis of systems is a part of the risk analysis. So, reliability gives us information how probable it is that failure will not occur, and the complementary is the failure function. And if you take this probability of a failure and multiply it or combine it with the severity of such a failure, then you get an idea what the risk is. Okay, so in our system we had seen a serial system where we had 3 resistors in a series. And what will happen when one of these is blocked, the whole system is blocked. So what will happen if we have so-called redundant elements which are there? So we have many, let's say, many examples of redundancy. So most of us have 2 eyes, most of us have 2 ears. Sometimes not in biological, but in technical systems, there are 3 redundant elements. So, and that means we have that current going through, and when will the current be blocked? So let's have the idea one element is failing, so still the system works. 2 elements are failing, the system still works. And in that case, we would say it is a 1 out of 3 redundancy. That means 1 has to work and 3 are there. Sometimes we need 2 to work, and in that case, it is a 2 out of 3 redundancy. Okay. The question now is, can we compute the failure function of such a system? So, failure function is Fs. How much is it? When we know the failure function F1, F2, F3, or the reliability two. Okay, in that way, we can say both are complementary, but we have to know these. So, where do we get such information of the failure functions of the individual elements? Okay, can you give me an idea? Where can I get that information? I need that for all elements in order to predict my system reliability or my system failure function. So where do I get that information? Can you give me an answer? Do you have an idea? Where do I get the failure function? Okay, that would be a typical question in an exam. So of course I can say maybe I have the failure rate here. So that would be an exponential distribution. Or I have the tau and the beta, then it is a Weibull. Or I just have some function which says reliability goes down over time, and then it's just some data I have, maybe not a model, but just some experimental data. Okay, but I need that information. And now the question is, how can I get the system reliability? And when will it happen that the system fails? Let's go back. System fails when? When does it fail? E1 fail and E2 fail and E3 fail. That means all three must fail. And what is the probability of the failure? Individually, again, it is F1, F2, F3. So I can say the probability the system fails is the probability that number 1 fails plus number 2 fails plus number 3 fails, and so on until element n. And so I can say Fs of t is the product of all failure functions of each individual element. And as I said, in the case of an exponential function, I can replace that Fe of t with 1 minus e to the power of minus lambda e t. And in that way, I can compute the system reliability. And because that is just complementary to the system failure function. It is also important to keep in mind that the failure function is not the failure rate. Yes, the failure rate is something derived from the failure function, and it is very important to distinguish, because the failure function, it is a probability over time, and the reliability is also a probability over time, while the failure rate is the portion failing per time, and as the name says, it is a rate. Okay, in that way, we have derived the failure function of the system. And now just let's imagine we have two resistors. And in the case of two resistors, we can modify, of course, we can modify here the formula, which says F is F1 times F2, Fs is 1 minus R1 times 1 minus R2, and Rs is 1 minus R1 times 1 minus R2, And yes, when we proceed here, we come to that formula. Rs is R1 of t plus R2 of t minus R1 times R2 of t. Keep in mind, if you compute a system reliability, the value you get must always be in the range of 0 to 1. If it's something larger than 1, then probably you have made a mistake. Okay, now in the case again of an exponential function and having two parallel elements of equal failure rate. That means lambda 1 is lambda 2. You can get Rs is twice e to the power of minus lambda t minus e to the power of minus 2 lambda t. And now, what is the failure rate for such a system? There are several possibilities. You could say lambda is minus dr of t dt divided by r of t. Or you could go the other way around. You could say mttf is the integral of rs of t dt, and then you integrate this, and then you end up by integration of that formula. mttf is 2 divided by lambda minus 1 divided by 2 lambda, and if that is an exponential function, that is 1 divided by lambda s. So in that way, and only in that easy case, we can compute the mean time to failure or the lambda system. But that is only easily possible when both elements have the same failure rate. So that means it is such a system. Okay, now that's something mathematical, and let's have an idea about redundant systems. In our example here, we can say, okay, there are two elements, both are carrying this current. For instance, that could mean you have not one cable, but two cables in parallel. One cable will break, or the interconnector will break down, so the second cable will carry the current. That is so-called hot redundancy, because both elements will work simultaneously. On the other hand, you have examples of a redundant element. Think about your car, or think about a car. In former times, cars had a so-called spare tire. So what is it? You get a tire puncture, the tire fails, you have to stop, you take out your equipment, you take out the exchange tire, and then you exchange it. So that is so-called cold redundancy. You have a redundant element, but it is not in place, it is not operational. You still have to install it, and okay. So these are two important cases. So then there is something in between. For instance, the redundant element is in a in a standby mode. Imagine you have something like the internet, and you have several servers, and these servers work in parallel. It's like in our HIS-in-1, for instance. Unfortunately, this operation of the servers in a hot mode, it leads to lots of exchange traffic because both servers must be up to date all of the time. So you could think about having a spare server which is just in standby mode. Yes, maybe you just update the data somehow, but it doesn't work as a server. And so if the first server breaks down, the second server will take some time and to take over, and then the second server will be operational. So that is so-called warm redundancy. So to tell it a little more systematically, in hot redundancy, all elements fulfill the same function simultaneously, 2 cables or such a thing. All system elements are therefore fully loaded with the same load. That's important because the load decides what your failure rate will be. So if you have a higher load, for instance, higher currents, higher temperature, higher mechanical loads, you typically have a shorter lifetime and a higher failure rate. And as this is so, both the reserve element and the primary element are having the same failure rate. So that's redundancy. In warm redundancy, the redundant elements are in a standby state. They are subjected to reduced operating loads. So the second element has a lower load. For instance, the server is not full up, but it is only in idle mode. So the failure rate is significantly lower than the failure rate of the active component, and the spare element can be ready for operation relatively fast. On the other hand, cold redundancy, I told you, the spare tire, for instance, is not installed. It is not loaded, so probably it will not fail, or its failure rate is 0 by definition, and it will quite some time to activate this element. Yes, that is important, and these factors you should keep in mind. For instance, if you have an aircraft, 2-engine or 4-engine, that is hot redundancy, all engines will work simultaneously. The warm redundancy is like this server, and cold redundancy is like a spare tire or something you have in storage to bring it out. So now here we have a more systematic way. That is just a single element. We have a series, so you could say if one fails, all fail. In that case, the reliability of the system is just the product of all reliabilities, and because RE is smaller than 1, RS is always smaller than RE. The series structure also leads to an addition of the failure rate. That's a parts count or parts stress method. Then we have here the 1 out of 2 redundancy. The reliability is just R1 plus R2 minus R1, R2. I'm always astonished when we look at exams. There are quite a portion of students just learning these formulas by heart. I don't think that makes sense, yes, but the important formulas are like these here, or you know how to derive a solution. So that is the 1 out of 2 redundancy. You can just derive it from Fs is F1 times F2, and in that way we have already derived it. For K out of N redundancy, where K must work and N is the number of elements, it's a quite complex formula, so we have Rs is the sum of N over E, R to the power of E, so all E are summed up from K to N, 1 minus R to the power of N minus E. Okay, that's hard to keep in mind, and in that way one can derive for such complex systems the reliability function. So using this, for instance, you can construct a reliability function for a complete system. So here you could say, again, here the reliability comes from this formula. So you multiply all reliabilities here, you multiply reliabilities E4 and E5, and you multiply reliabilities of E6 and E7, and in that way you get a simplified system. And again, here you have the redundancy, then you get system like that, and in the end you have something like this. Okay, so you just simplify it and you put together with the formulas you know in order to just simplify it stepwise, 1, 2, 3, and then you have only a 1 element system. Okay. Sometimes we have a problem. For instance, when we have 3 elements and all 3 elements must be compared in a certain way. So, for instance, if you have elements 1, 2, 3, and one just fails completely, that is easy to detect. But imagine all 3 elements would be sensors. And one of the sensors would be different. Okay, and in that way, you have to know that something is wrong and you have to deal with the situation. And the easiest way you can have is just having an alarm. So you have different indicators, and one of the indicators is different. In that way, you could set an alarm, and that is called, on the other hand, when the system also decides what element is wrong, then you have so-called majority redundancy. So 2 are still working, 1 is not working. You have a additional element, and in that way your system can know at least that something is wrong. There are other elements. For instance, you have a bridge structure. A bridge structure is something which is important. Let's first simplify it in a way we have just here bridging. What would be the result? Imagine we have two elements. And for instance, that would be a sensor, and that would be a microcontroller, for instance. Okay, so we have that system, but we say that is not reliable enough, so we do it twice. What is the disadvantage? We have 4 elements, and if one of these elements fails, for instance, if sensor 2, sensor 1, YC1, YC2. If one of these fails, all of this is also broken. You cannot use the microcontroller anymore. And to that purpose, it is better to have some kind of bridging structure. And that bridging structure would make it possible that your current you have is something like this. It goes here, it goes here, it goes here, and it can go here, or it can go up here. So that means if that element is broken, also the current will come along here, and you still have an operational system. So to that purpose, you have that cross structure, but on the other hand, you often need an additional element here, and that additional element can be in between. So you can have both directions, but you also can have an element which only works one direction. So you can say, okay, it only goes this way. And there are other possibilities, for instance, where the same element appears twice, also it exists only once. Okay, let's say these will not be regarded anymore. I think that is an important structure here. You have to keep in mind. And now let's go to further things. Imagine again we have sensors, and both sensors indicate something. For instance, in an aircraft we have an important sensor which is a speed sensor. The speed sensor gives us the indication of the velocity of the aircraft, and in an aircraft it is, for instance, air velocity. Or airspeed. Why is it airspeed which is relevant and not speed over ground? Because the buoyancy you get is a result of the speed you have in your aircraft. In that way, it is relevant how fast you are relative to the surrounding medium, like the surrounding air, or in a water vessel, possibly the water. So in that way, the speed. What will happen if your speed is too low? Then you get a stall. Yeah, your aircraft will not fly anymore, it will just drop. Too high. What will happen if you have an aircraft, let's say like an aircraft from 1920, and you fly it with 1,000 kilometers per hour, then it will just be disintegrated, it will fall apart. So you have a structural disintegration. And that means you have two limits, low and high, and you must stay in between these limits. So the most crucial mistake a pilot can make is flying too slow, flying too fast, or flying too low, for instance. But now we are talking about airspeed, and in that way you could say, how do we measure airspeed? So it's something like the pitot tube, and you measure the pressure against the surrounding air, and that pressure will be the higher, the faster your aircraft is. Unfortunately, a pitot tube, it can be blocked. Yeah, you can have some particles coming in, for instance, an aircraft flying in a dust storm, for instance, or you can have icing of the pitot tube, and in that way you could have two such sensors. And now, if one of the sensors fails completely, for instance, if that sensor says, okay, 0 speed, and the other still shows you a reasonable speed, you could say, okay, one of these is wrong, the other probably is right, and in that way, you could go after that decision. In other cases where they are just different with their signals, you have a problem. Some systems just have to be turned off. For instance, imagine you have a chemical plant, you have a reactor, different sensors show different results. What will you do? Turn off operation, yeah? Reactor or something like this. Yeah, okay. So we are in an aircraft, we have two speed sensors. We are flying at 400 miles per hour, and now we turn off our engines and say, okay, the system is out of order. No, not such a good idea. We have to make provisions that this will not happen, so we can take 3 sensors. Probably only one will fail. Yes, so you could say just a guess, that is 100, that is 400, and that is 402. Okay, so you would say, yeah, these are right. And that is wrong. But again, you need something to decide. You must have a majority voting system. And this says, okay, one is wrong or failed or faulty, and 2 and 3 are functional. So in that way, you can keep your aircraft flying. Okay, now let's think a little more about our aircraft. I told you we have the pitot tube and we have 3 pitot tubes. And now you have icing. Icing is due to weather conditions. So that means we have high humidity in the air and low temperatures around, and because in a high speed flow, you have a static under pressure, and that leads to cooling, and that further cooling leads to condensation. Okay, so we have condensation on all 3 pitot tubes. Question is, now will it help us that we have 3 pitot tubes? Of course, it will not help us, because the same failure will happen to all pitot tubes. And that is often a severe problem. Also, we have so-called triple modular redundancy. If all elements work in the same way, have the same technology, same mode of operation, then we can still have problems. Okay, so to that purpose, majority redundancy is combined with diverse redundancy. Diverse redundancy means we have different types of transducers. For instance, we have a pitot tube, pressure sensor. We also can use ground speed. Possibly it's not precisely as airspeed, but we can get it from a GPS, for instance, global positioning system. What is also possible, we get that information from a virtual sensor. So that means we have a mathematical or physical model of our aircraft. And that just computes. So that means all information I have in that aircraft, for instance, the attitude of the aircraft, and from all of these data, I also get some virtual speed, and I can compare it with the speed of a pitot tube. So in that way, we have many possibilities to lead to diverse redundancy, and such use of also virtual sensors is very important in order to improve the quality of the data on which such voting decisions are taken. And now looking again at icing, yeah? The icing is a common cause, yeah? So temperature, humidity, speed altogether lead to icing. The common cause is the weather. The common mode of failure is icing, yeah? So you can say here, cause and the mode is ice. And in that way, we can have many phenomena. For instance, we have a stroke of lightning, that's a so-called surge. So that surge goes into all of our electronic systems, and so many parts can fail here, and in that way, by surge or stroke of lightning, redundancy is lost. Yes, we can have excessive G-forces in a crash, for instance. So the crash is so severe that all of the electronic systems which would inflate the airbag would fail. So in Fukushima, where we had that heavy reactor accident, all of the emergency power supplies were flushed with water by a tsunami. So all of the emergency systems were too close to the sea. The tsunami wave came and it flushed all of the diesel engines which give emergency power to the system, and in that way the complete Fukushima system broke down. And in that way it is important to avoid common mode events and common cause events. For instance, there could be other phenomena. For instance, you have a fluidic system, and in order to avoid that when one fluidic system is blocked, you make two in parallel, and unfortunately you have some particles in the reservoir you want to pump. So these particles could again block both pipes you use, and again that would be a common cause and a common mode failure. Yeah? The use of diverse redundant mechanisms allows us to achieve higher safety integrity than identical redundant mechanisms. Another example is, for instance, in high reliability and high safety systems, like for instance in aerospace, where we have astronauts, we have redundant systems. For instance, computer systems, there can be 3 or 4. These computer systems have different hardware. So maybe one is Intel, the other is Motorola, and what else we can have? AMD. And also the programming must be in a different way. For instance, you have different programming languages, and the programming languages are also from different suppliers. In that way, we avoid systematic errors. We had these roughly 20 years ago. There was a systematic fault in Intel processors. Under some conditions, these processors just computed wrong values in, I think, in a multiplication. And now if you have 2 such processors, redundancy will not help you at all. And so in that way, diverse redundancy helps us avoid systematic errors, systematic faults, and systematic failures. Okay. Now we have seen the reliability block diagram. There is another mode of representation which goes back to Mr. Boole, and in that way you can combine certain events. And that is some representation which is complementary with the reliability block diagram. For instance, we can have a so-called fault tree. In the reliability block diagram, the function is modeled. In the fault tree, the failure event is modeled. And imagine we have 3 redundant elements, and the main event will only happen when all 3 basic events will happen. For instance, that basic event could be failure of the first redundant element, or the second redundant element, or the third element. Each would be described by a certain probability of failure, and so just multiplying again all probabilities means that is an AND. Means we multiply it, and so failure 1 is 5 to the power of -4 as an example, times 10 to the power of -3 is 5 times 10 to the power of -7, multiplied with 1.5 times 10 to the power of -3. So we end up with a very low probability of that event, which is just 7.5 times 10 to the power of -10. So again, that would be quite improbable, and in that way you could model something like redundancy. So all failure events must happen, and in that way it is not called failure tree, but it is called fault tree. The difference is when we have 2 things which can happen, and if either or happens, so that is an or. And here again you could say when will it happen? In the case of very small probabilities, you can roughly add these, but if you do it correctly, you say RS is R1 times R2, and again Fs is 1 minus 1 minus F1 times 1 minus F2, and in that case that would be 0.999, that would be 0.999. What is that? You just take away 1 promille of this. That is 0.998, and 1 minus okay. Again, that is roughly the result. But for very small failure probabilities, you can do it similar to the failure rates. You just add them. In that way, we have a different representation. So often for just to show graphically what can happen, we can have such complex fault trees. Again, the fault tree will go down here, and it's like a tree with many branches and sub-branches and sub-branches and so on. And in that way, we can again compute reliability and failure probability. It's the very same mathematics like in a reliability block diagram, just the representation is different, and we must say fault tree models failure, reliability block diagram models function. Okay, now we would like to address again our system where we have redundancy and we have a cross interconnection. We leave out that system. And now I would like to show you a systematic method how in systems which have many elements we can compute the reliability function and the failure function. And we have 4 elements, and each element can be functional or failed. Often we say it is up or down. That is equivalent. Okay. And so we could also say, okay, that is a 1, that is a 0. And so we have binary for each element we have binary states, and how many combinations do we have? Of course, it is 2 to the power of n. N is 4 here, so we have 2 to the power of 4, and it is 16 combinations we have here. So such a system can be in 16 different states, and now we would like to see what is the probability for each state. And in that way, we build up a table. So first of all, we have seen we have case 1 to 16, and we have all of the 4 elements. And now what can we do? For each, we can make all combinations, so we can make it just in an easy way that can be done by a computer. We say, okay, in the first 8 cases, element 1 is up, and in the other 8 cases, it's down. For the element 2, we say, okay, for 4 cases, it's up, another 4 cases is down, cases 8 to 12, 9 to 12, it's again up, and so we combine this, so we have here 1, 1, 0, 0, and in that way, we get all of the combinations from 1, 1, 1 to 0, 0, 0, where all are broken. Please note that is just making the combinations. That doesn't tell us anything if it is possible at all to get from a certain case to another case. That must be decided on the base of the system structure. What we can also do is we write a short code. For instance, element 1, 2, 3, 4, we just write them. If it's down, we just make it an underscore, and in that way we can say, okay, we can describe it easily. Again, binary system. And now the question is it functional? Often that is easy, but here we can say, okay, when all work, the system will work. When all are failed, system will fail. But what is it when we look at intermediate states? Okay, if only one is defective, and no matter which one it is, the system will work. Okay, so we can say here in that case, just one system will work, system will work, system will work. Here it will work. and here it will work. So that's all 4 cases where 1 is okay. But on the other hand, when will it work also when 1 and 4 is okay, when 1 and 3 is okay, when 2 and 3 is okay, or when 1 and 4 is okay. So we have many combinations. On the other hand, if we wouldn't have that cross interconnection, we would have less combinations where the system will be operational. So in that way, we can say also if 1 and 4, 1 and 3, 2 and 4, and 2 and 3. That means in all cases where we still have 2 elements, there is only one case which doesn't work, when 2 on top and bottom. So here that doesn't work, and which else? Yes, 2 and 3, and that also doesn't work, yeah? And in that way, we have many combinations where it will work. Now, what is the probability here? The system can be in one of 16 states. The total of all states is 100%. So with a probability of 100%, the system must be in one of these 16 states. So you could say sum of pi is 1. And that is important. And now, what is the probability that 1 works, 2 works, 3 works, and 4 works? Then we just multiply the reliability functions. What is the probability that 1 works, 2 works, 3 works, and 4 works not? It's reliability of 1, reliability of 2, reliability of 3, times failure function of 4, and again we can say that is R1, R2, R3, and in that way we can get all of the information. What is the most important information we need? We must know that is the basic information. Without such information, we cannot get the system's reliability. So we must know the reliability of all ingredients here of our complete system. Another thing is, what is important, it is to see what is the probability of the individual state. And again, that's relatively easy because we just combine these values. But the question is, the system functional must be based on this reliability block diagram or on the fault tree. So that is really, let's say, the engineering question. Is it functional? Is it up or down? And now what we can do is we can say the reliability of the system is the sum of all individual reliabilities in the case when when the system is up. And the complementary is the failure function. But we can also say the failure function is the sum of all where the system is down. Again, you can compute it in both ways, but in the end, when you check it, if S must be 1 minus Rs, if that is not the case, you have done something wrong. And the total, again, it must be just 1. And in that way, you can compute the reliability of systems which are complex. Unfortunately, we have a problem here when we want to go for that state space method, and when we have many elements, we will have a problem because, for instance, imagine we have, let's say, 32 cases, so 32 elements. That means 2 to the power of 32 cases. And that means we have very many cases, and in such cases it is only possible, yes, maybe it's still possible to get the individual failure functions for 32 elements. That's not too hard, but it is quite hard to judge all of these combinations and to know is the system functional or not. So in that way, it's a universal method, but when we do it by hand, it is just limited by the number or by the size of the matrix we get here. Okay. In that way, we can compute the reliability of such a complex system. In that way, we have a very versatile and a very effective method for quantitative analysis of mean time to failures, of failure function, of reliability over time. On the other hand, that's just mathematical manipulations based on the system structure. But in real life, we often have many phenomena. I just give you an example. In the clean room, we have a pump. The pump uses silicone oil. Yeah? The pump leaks. That leads to contamination. That leads in a sputter leads to a sputter adhesion, which is low. That leads to, when you make a metallization in a sensor, it leads to So, and then you can have a system failure. Unfortunately, that's a sensor in an aircraft. The aircraft will fall down. And what was the basic cause? We had a leak in a crucial pump, and that cause could have an effect. It could lead to contamination of a sputtering machine. The sputtered layers are not adhering, and so on. So that shows us we can have a chain of events, and in that way, the idea was how to find out if such a basic event on a very low level of technology can lead to system failure. And in that way, the NASA introduced such a method, and that's the so-called FMEA, failure mode and effects analysis, and that's still one of the most important risk analysis methods. Initially, there was only a product FMEA, so that just could show, for instance, what does the silicone oil have an effect on adhesion or such a thing. On the other hand, no, that's a process FMEA, and we have a product FMEA, which is more on the level of a system structure. If that fails, will that fail? And in the end, the number of layers was not as high as we have it here, but we have many layers and we combine both, and then we have a so-called system FMEA. We also must say that such system FMEA was not possible maybe, how many, 60 years ago or so, because people didn't have that computational power, people didn't have personal computers, so all of this was to be done by hand. But the main idea is, in our company we have experts. We have, in different departments, we have staff, and this is, for instance, from development, from construction, from laboratory, so research. We have test engineers, we have the manufacturing, we have the industrial engineering. Industrial engineering is people who bring, let's say, research and development into production. Yeah, so they are some kind of interface, so they industrialize technologies. We have sales, maintenance, and so on. And from any level of our company, so it can be a worker, and it also can be a manager here. All experts, and sometimes we even have external experts. So in America, it is much more in use to use external experts. So often they hire some professors in order to give some expertise and to give bring in their knowledge on a high level. Okay. Here we have the external and internal experts. We need one who is an FMEA method expert. That either can be the person responsible for the FMEA, or it can be a different person. That is mainly depending on the size of the project. So normally you have a project, you have a sub-project, and for instance, in the project, let's say for Elon Musk, he has an aerospace company, and they have the project of relaunchable rocket. And for that relaunchable rocket, we have a project FMEA, or risk analysis for that rocket. And then we have a person who is a project leader for the FMEA project. Above him is Ion, or who else the project leader for the rocket is. Okay, so here we have this ring of experts and of specialists on FMEA, and they work together, and it's not just having coffee and tea together, but they must work together in a systematic way. And in that way, it is important that the system they evaluate is structured. Please note, FMEA is a bottom-up method. Okay, I was here, pump leaks, that's the bottom here. I should have painted it the other way around, so it's bottom-up. Up to system level, that is meant by bottom-up. So as I said, we have a product development, we have a process planning, and so we have a FMEA of process and a FMEA of product, and both together give the system FMEA. Okay. Now, the idea here is, as I already said, we have on a lower level a failure cause. That failure cause leads to a failure on a higher level towards the system top, and the failure has a result. And now we can say the result of a failure is a failure on the next level. And in that way, a failure propagates just in the 3 steps: cause of failure, failure itself, and result of failure. But we have to assign this to something, and so we have 5 steps of FMEA, which is very important, and you can be sure that it is quite probable that I will ask for the 5 steps of FMEA. So the first thing is the system elements must be brought into a structure, and that is in a hierarchical way. So, for instance, you could say you have a car. In a car, you have, for instance, powertrain. You have the cabinet. You have the, what else do we have? Powertrain, cabinet, maybe comfort, and so on. And for the powertrain, you could say, what do we have here? We have the gear, we have the engine. The engine again has a controller. It has the motor itself, and so on. So the system is structured top-down. For the comfort, you could say it in a similar way. For instance, you have some heating, and you have some sound system, and so on. So you can structure it top-down, again, like a tree. To these structural elements, you assign functions. So you ask yourself, what is the function of the powertrain? So you can say, yes, of course it's to lead to some propulsion of the car, yeah? And. What is the function of the cabinet? So it's protection. Again, protection against what? Protection against weather, protection against impact, protection against stones, and so on, yeah? Dirt, comfort. What is the function of comfort? Yes, keep it warm, keep it smooth, and so on. So you have functions. On the other hand, yes, so you can assign functions here. So you say propulsion, so here it's a shelter, comfort is warmth and so on. So that is a function. What is when it doesn't propagate your car? So then you have failures. So failure is non-function. It's a complementary of function. So what? Well, when it doesn't shelter, so here you could say it's some stop, or for the shelter it rains in, and so on. It's too cold. So that would be the failure. Function is not fulfilled. And for all of these definitions, you could say you can do this on every level of your system. And for each of these combinations, you assess the risk. What is risk? Risk is probability times severity. On the other hand, the people who invented FMEA, they defined risk in a more extended way. They said we have the risk priority number, and that is probability times, no, that's O, it's occurrence probability times severity times detection probability, OSD. So that's a prop. That's severity. But sometimes I can build something in, I can make a check, yeah? That check will not prevent that such a thing happens. For instance, the oil pump leaks, okay, that is not prevented, but we can detect it. And so that's a detection probability. So that's a probability of the failure. The severity is related to the failure effect, and the detection probability is related to the failure cause. Okay, and so we can make such an assessment for each of the system elements, so that you could say you do for all together, and after you have found out the individual risk priority numbers, you must optimize your system. So that means make system better. That means improve. So FMEA is helpful insofar as we know what can go wrong, but that's not the complete approach. The fifth is optimization. We do better, and then, of course, again, we have to assess FMEA, assess risk priority number, because we want to avoid either probability of some failure, or we want to avoid that it has a severe effect. So just to show you here, we have a system, we have the system elements I was showing you on the car, we have the system elements, and you can just say SA1 and SA2 are subsets which together give system element 2. So that is a subset, so that is a set, a subset, and that are subsets, yeah? So you could say the gearbox is a subset of the powertrain, and the powertrain is a subset of the car. And in that way, we have just these combinations like in a tree. On the other hand, we have so-called interfaces. For instance, let's say we have the powertrain and we have, for instance, the suspension. And sometimes we need information from one branch to the other branch, and that is done via a so-called interface, yeah? Or for instance, let's say in a comfort system we have some sensor which notices the car is not running smooth, and that sensor gives its information to another subsystem of the car. And then we have a so-called interface. That means we have a connection, or we have a possibility of failure propagation, not in a way that we go up the tree, but we go sideways some way. So that's a so-called interface we have in such a system. And but what is important in FMEA system is structured top-down. But the failure propagation it is bottom up. So we look at the system, car, what is it assembled from, and then we go down until we go to the smallest screw in our car, if you want so. And on the other hand, when we look at the screw and say that screw is breaking, what will be the effect? Is it the screw in in your steering wheel, so suddenly you got your steering wheel in your hand and no longer attached to your car, for instance. In that way, you could make a FMEA to find out if that can happen. Okay, and again, we can say we have functions go to a higher level. We have internal functions of the system element, and we have ingoing and outgoing function via so-called interfaces here. Now we assign functions. We say, okay, what's the function of the car? Of course, that is a list, yeah? That makes it so complex. And what is the functional contribution of system element? What is it of system element 2 and of the subsystem? Here again, we have a functional contribution of system element 3.5 via interface to system element 2. And in that way, we can assign the functions. Then a non-function is a fault or failure. Unfortunately, for one certain function, we can have different types of failures. That again makes it more complex. Yeah. So you cannot just say non-function is a certain failure, but you have to look which kind of failure is it, and will it mean a non-function? And in that way, we can have the faults or failures. Again, we assign these, and now for each individual thing we have, for each system element, we can make this overlap: failure cause, failure result. Failure on a lower level is a failure cause on a higher level, and in that way, a failure propagates through the system. But still, the basic cause is the leakage of the pump, for instance. Another example, photolithography has excessive tolerances. We have large variation of individual resistor lines on a MEMS membrane. Wheatstone bridge is not balanced. What is the result of that? Pressure sensor has excessive uncertainty of measurement. And if that happens, the anti-brake locking system of the car will not work properly. For instance, it will block a wheel while it should unblock it or something like that. And again, you could say, what is the effect of defective photolithography on the safety of the car and the safety of the passenger? Now, let's have a look at that, at these three parameters. O is occurrence probability, S is severity, and D is detection failure probability of the failure cause. So D is assigned to cause. Severity is to the result of the failure, and the occurrence probability is to the probability itself. So we assign it from 1 to 10. That means low to high risk. Again, a low value, 1, is good, it's excellent. Low severity is it will not harm anybody or anything, no harm. And the detection probability means if it's 1, it can be detected easily. You see it evidently that there is something defective, and 10 is bad, so it's hard to detect the failure cause. And in that way, all 3 values are combined, so RPN is OSD. Typically, such a sheet is made. Here we have the process function, a description, failure mode, effects, then we assign severity, and in that way we can make a sheet. Such sheet is typically prepared for each individual system element. So where do we have it? Okay, in the worst case we have to make 1 sheet for each system element, and again here we have severity, we have occurrence probability, detection probability, here we have the RPN, and the next thing is what will we have to do about it, who is responsible, what have we taken, and how is severity, occurrence probability, and detection probability after action. Okay, here that sheet doesn't only show us the improvement, but it also shows us the state, but also the improvement. Okay. Maybe we go a little further through that stuff in the week to come. For today, I would like to thank you for your attention and see you next week.